All right, so that's the title of my talk, which unfortunately isn't centered, and it's a bit misleading because solids also includes shapes, 3D shapes like cylinders and spheres, which you can't reproduce exactly, but you can approximate quite well. For example, cylinders you can approximate with a prism with a lot of lateral faces, and a sphere you can approximate with a geodesic dome, again with a lot of faces. The other thing on that slide is my Twitter handle, where I post a lot of cat pictures, like many other people do, except my cats kick their cats' asses. This is going to be a bit mathy, but and I know a lot of people kind of dread that kind of thing, but I hope that by the end of this talk, you won't all be sleeping. And I told you my cats kick ass. 3D. But in order to get 3D, you need to get 2D first. So we're going to start with a short recap of 2D geometry. And first of all, let's see what a polygon is. Well, it's just a closed broken line in a plane. The second thing about it is that it has only straight lines as edges. There are no arcs. Also, I'm very smart. Click the wrong thing. Don't separate navigation. Lesson learned. The number of vertices equals the number of edges. And the last thing is that you can't have 3 successive vertices on the same line, because that's not going to be the polygon you intended anymore. So this is just words, and as you've seen, we're going to draw a bit. Now, this is the first thing that people think of when they hear the word polygon. It's something like this, and this is a convex polygon. A convex polygon is a polygon that has no angles greater than 180 degrees. A polygon having angles greater than 180 degrees is going to be something like this. And this is a concave polygon. Both convex and concave polygons are part of a bigger class called simple polygons. Now, polygons that aren't simple aren't exactly called complex, because complex relates to something else. Think complex numbers. And in order to get that, it's something like when I got attacked by a stray dog and it ripped off one of my boots. So I returned home on complex high heels. One was real and the other one was imaginary. Same with complex numbers. They have a real part and an imaginary part. So polygons that have an edge intersecting another edge of the same polygon are called self-intersecting. What a surprise. So self-intersecting polygon is something like this. And it looks kind of like a ribbon. You know, no, my Jerry doesn't have a ribbon, but I do have another T-shirt with a ribbon. The best known type of self-intersecting polygon is something like this, right? And this is called a star polygon. Now, a star polygon is a bit different from a star-shaped polygon, because a star-shaped polygon is something like this. And this one is not a self-intersecting polygon. It's just a particular case of a concave polygon. These are a lot of polygons. We're not going to be using them all today. So let's see which ones we're going to be using. First of all, triangles, all types. Then we're going to have parallelograms. Parallelograms are polygons with 4 edges and obviously 4 vertices. Opposite edges are equal, and so are opposite vertices. Opposite edges are also parallel. And adjacent vertices add up to 180 degrees. Adjacent angles add up to 180 degrees. Then we have a particular kind of parallelogram, which is called a rhombus. A rhombus has all the properties of a regular parallelogram, except it also has all edges equal. Narrowing things down even more, a particular kind of rhombus is the square. The square has all the properties of a generic rhombus, only it also has all angles boiling at 90 degrees, unlike my water, which boils at 100 degrees Celsius. Now, let's CSS these things. That's a rectangle, and everything starts from a rectangle. If we give it this thing equal width and height, we're obviously going to get a square. Now, if we have our initial rectangle and we do something to it, let's say we apply a transform, a skew transform in this case, we're going to get a parallelogram. And this parallelogram is going to have angles of 90 degrees plus and minus the skew angle, which is 15 degrees. So that's going to be 90 degrees plus 15 degrees, that's 105 degrees, and 90 degrees minus 15 degrees, which is going to be 75 degrees. Now, since a rhombus is just a parallelogram with equal edges, with all edges equal, now, if we give this equal width and height, we're going to get a rhombus, right? Come on. Don't you have an opinion, a spine? Are you at the wrong conference? Or is this the wrong talk? Sorry, I'm here. Well, if this is right, then explain this. Does that thing have all edges equal? Well, not from our point of view, it doesn't. But first, let's see what transforms do. This is my friend Boo, and I've used him for another talk. That one wasn't about 3D in particular. It did have some transform parts, but it was mostly about SAS and all. And somebody drew him, somebody with quite a bit of talent. But I was absolutely mortified because that drawn Boo also had fangs and claws. And that's not my Boo. He doesn't have fangs and claws. He's not going to come and eat you, rip your heart out, and drink all your blood. He's just a friendly little Boo. And just like any other DOM element, he has a system of coordinates, his own local system of coordinates. So let's say we apply a transform to Boo, let's say a skew transform, like we had before. And I should learn to apply something more obvious. That's better. Sorry, Boo. You can see that not only does Boo get skewed, but his system of coordinates gets skewed along with him. And the same thing happens if we apply a rotate. His system of coordinates gets rotated as well. And if we apply a translate, now, that was very smart of me. It's obviously going to work, but with different units. His system of coordinates gets translated as well. This is one thing that proves itself pretty useful when you want to have a chain of transforms having different transform origins. And what I mean by a chain of transforms is that you put one transform after the other. Something like this. Now, the last function is scale, and with scale it's not so obvious, but think of it this way. This system of coordinates has a unit value. This unit value is increased. So this leads to something very interesting when you inspect scaled elements in DevTools in different browsers. Because in Chrome, in the box model, you're still going to see the initial width and height you gave it. While in Firefox, you're going to see the value after multiplying with the scale factor. The scale factor in this case is 2. So if you have an element having a width of 300 pixels and you scale it by 2, you're going to see for the box model in Chrome, you're going to see 300 pixels, the value you gave it. But in Firefox, you're going to see 600 pixels for the box model. But this was mostly about skew. And the thing is, from the elements inside the transformed element, nothing has changed. Because you've probably seen this thing. When you apply a transform on an element having children, the children, and all descendants in general, get transformed as well. So from the inside, nothing changes. And if you have a skew or something, you see that the axes are not perpendicular anymore. But from inside the element system of coordinates, you can't see that. It's like we're on the Earth, but we can't perceive the rotate transform on the Earth. Our senses can't tell us about that. We can compute it, but that's a different story. So a bit more in detail about the skew transform. So this is a square, and we apply a skew transform on it. And the skew angle is the angle between the initial axis that is perpendicular onto the skew axis. The skew axis is the x-axis in this case. So the other axis is going to be the y-axis. So the skew angle is going to be between the angle between the initial y-axis and the y-axis after the transform. So this angle here. Also, if we have a random point of coordinates x and y, only the coordinate along the skew axis gets changed. The other coordinate gets preserved. So the x-coordinate gets changed by a value a, which you can see it depends on the angle because it increases with the angle. And when the angle is negative, it gets negative as well. So you have this thing, but this is the original edge perpendicular onto the skew axis, and this is the one after the skew. So if we want this thing to have all edges equal after the skew, we need to scale down these lateral edges. So we're going to have to do a skew along the y-axis. But by how much we need to skew this thing? Well, there's a bit of trigonometry involved. And we have to compute a few things in a right triangle. And there are just 4 formulas, and these are all you need to know in order to compute all the stuff for 2D and for 3D, everything. So it all reduces to a right triangle, and these formulas where c squared is a squared plus b squared, and c is the hypotenuse, and a and b are the other 2 edges. And also we have a few trigonometric functions, the sine, which is of alpha, which is a over c, and the cosine of alpha, which is b over c, and the tangent of alpha, which is a over b. So knowing these, we can apply this for a particular skew x. So this is the original edge, and it's L. So this piece here is going to be just half. So it's L over 2. And this is the final edge after the skew. It's going to be M. So this piece is M over 2. And this is the angle alpha. And we can compute this alpha because we can compute its cosine. So its cosine is going to be L over 2 over M over 2. So that's L over M. So we got the ratio between the edge before the skew and the edge after the skew. So if we have, going back to this, not so far, just to here, and we have 60 degrees, then we need to scale this along the y-axis by the cosine of 60 degrees, which is 0.5. And we got a rhombus. This looks pretty plain. So let's give it a background. Let's say a linear gradient background. So you can see this blue part, this is a triangle. So a triangle is just half a rhombus. Well, let's see how we can CSS this in another way. So we obviously start with a rhombus. And then we take a rectangle or a square, it doesn't really matter. But one edge of this rectangle or square has to be equal to one of the diagonals of the rhombus. And this is going to be another element, a child element of the rhombus. So then we cut out everything outside the rhombus, and we got a triangle. Let's see how we CSS this. So first we make the pseudo element visible. And you can see it's transformed. So we need to reverse the transforms from the parent. So we reverse them in the reverse order as we apply them. So it's first going to be a scale y of 1 . This is a bad way of selling something. And this is going to be something like 1.15. And then it's going to be a skew x. And this is minus 30 degrees, because that was 30 plus 30. So it's minus that angle. And then we have a rotate. And again, this is going to be minus the rotate angle. And of course, there's an S missing, which is why it's not working. And we got our square, but it's not positioned as before. And for that, we need to translate it up. This is minus 50%. And we got just the thing from before. So this thing inside is our triangle. And to wrap up with 2D, there are a few things to remember. All elements have a system of coordinates with the y-axis pointing down. Transforms affect the element's system of coordinates, and they also affect all its descendants. A skew of angle alpha results in a parallelogram of angles 90 minus alpha and 90 plus alpha. And a skew only affects the coordinate along the skew axis. And the sides along the other axis get longer following a skew. So now let's move on to 3D, because that's actually my topic. And let's build something in 3D. For example, a cube made out of pyramids. We have a pyramid coming from the bottom, one from the left, one from the top, one from the right, one from the back, and one from the front. Pyramids. But how do you build a pyramid? Are you alive? Yes. A pyramid, but not the ones in the background. My time is limited. Those took 20 years. So we're going to have a square base. And we're going to have also 4 lateral faces, triangular faces. And we know the height, the edge of the square base. And we also know the height of the pyramid, because it's going to be half the edge of the cube, which is equal to the square base. But there are other things we don't know. We don't know the other 2 edges of the lateral triangles. How do you compute those? Well, again, it all reduces to a right triangle. So in this case, this is the pyramid height, and this is one of the lateral edges. And this is going to be half the diagonal of the square base. And this is a right triangle, and we use it to compute stuff. For example, the lateral edge squared is this height squared plus half the diagonal squared. But what is half the diagonal? Well, again, a right triangle. This is the base, the square base. This is one edge, this is another edge equal to it, and this is the diagonal. And it's obvious that the diagonal squared is twice the edge squared, the base edge squared. So knowing these 2 things, now we know the lateral edges. But in order to get a rhombus and a triangle, we need to know the angle between those 2 lateral edges. So the vertex angle for a lateral face, we also get it from a right triangle. What a surprise, right? So half the sine of this angle is going to be a over 2, half the square base, over the lateral edge. So knowing all these things, we can build the lateral triangle. And we're not going to do that again, because I already covered that in 2D. We're going to move on to positioning the faces for the pyramid. So we first have the base, which we're going to rotate from the vertical plane into the horizontal plane. And we want the face, because this has a face and a back, to point down outside the pyramid. So that's going to be a rotate around the x-axis by minus 90 degrees. By plus 90 degrees, it would be pointing up. So the face would be inside the pyramid, and we want it outside. The lateral one, so first we need to translate it forward with half the edge of the base square. In this case, half of it is going to be 5 ems, if I recall that correctly. And it's in front, but it's vertical. We need to rotate it around its x-axis, but by what angle? For that, we need to know the angle between the base and one of the lateral faces. And again, we find that from a right triangle. So this is the height, and this is half the edge of the base, and this is the angle. So we're going to get this angle from the tangent of its angle. So it's going to be the height over half the base. So in this case, it's going to be 45 degrees. So we need to rotate this lateral face by 90 degrees minus this angle between the lateral face and the base, which is 90 degrees minus 45 degrees. Oh, I went back too much. Is also 45 degrees. So it's going to be rotate x 45 degrees. And this is just for the face in front. But if we rotate it around the y-axis before everything else by 90 degrees or something like this, it's going to be on the right. And if I rotate it by minus 90 degrees, it's going to be on the left. By 180 degrees, it's going to be in the back, 180. This is a bit hard to observe. So to make it more obvious, we can put something like a rotate transform on their parent, the pyramid itself. So we're going to have transform, rotate, y, a certain angle, and this should rotate the entire pyramid. Except the whole thing looks broken now. But that's not a problem. This is normal. And let's see why. Bam. We have a frame with two doors that are animated in 3D. The frame is not animated yet. Let's animate it. And now the frame is animated, but the doors look all wrong. They look flattened in the plane of the frame. And they look as if, you know, my Jerry dropped something heavy on Tom, and Tom got flattened. That's how they look. And that's kind of what had happened. They did get flattened into the plane of their frame. And this is because of a property that you can already see in the title, because I was stupid enough to put such a title and not to write this correctly. And this property has a default value of flat. But as Tom shakes himself to come back into shape, we can fix things with a value of preserve 3D. And now the frame is animated, and the doors are also animated in 3D. So this is what we need to do for our pyramid as well. We need to add a transform style preserve 3D. And now it's in 3D again. Now, next step after creating the pyramid is to position it on the cube. So the first pyramid, you can see this is the center of the pyramid, and it's in the center of the cube. So to position it on the cube, the first thing you have to do is translate y half the edge of the cube. And this is just for the bottom pyramid. If you also apply rotate of 90 degrees. That's not where I meant to put it. Nope, that's not what I meant to put it still. Jeez. All right, so this is 90 degrees, minus 90 degrees, 180 degrees, and again I did over 1,000, so that's, and 90, but not 900, I didn't delete the 0, rotate x, and this is 90, and minus 90 is going to be in the back. So let's make this a bit more interesting. And let's say we have the following animation stages. First of all the pyramids are closely packed and they form a cube. Then they move outwards along their own y-axis. And then they rotate by half a full turn around an axis that's perpendicular onto the y-axis. This can be the x-axis or the z-axis, it doesn't matter. Any of them is good, or any other axis in their plane. Whatever works. And then the pyramids move back inwards by the same distance they moved outwards. And it's also going to be in the same direction, because by rotating the entire pyramid, we've rotated its system of coordinates. So let's see how we code these animation stages. So first, let's say we move this outwards, and we're going to have another translate y by 5ems. But we're not going to do it like this. Unlike skews, for example, translates are additive. So if you have a skew 30 and another skew 30 degrees, you can't add those up and get a skew 60 degrees. That's not additive. However, translates are additive. So you can have this as being just one translate of 10ems. And the next thing we do, the next stage, is going to be a rotate. And that's going to be by half a full turn. And in case you haven't seen this before, this is another unit for the rotate. There are turns and there are also radians. For example, 3.14 radians is the same thing as half a turn or 180 degrees. I think half a turn is most intuitive here. And then we translate it back by 5ems. So we have another translate y of 5ems, and it moved back onto the cube. So now let's turn all these stages into keyframes, and we're going to have something like this. So it moves outwards, rotated, moves back. Now this is just one pyramid, so let's see how the final result looks. This is gonna Okay, what did I do? Oh. Okay, this is the cube exploding, and then it recombines into a shape that's called a rhombic dodecahedron. This is a shape having 12 faces and 12 rhombic faces. And at the vertices of the initial cubes, there are 3 rhombic faces meeting, while at the vertex of each original pyramid, there are 4 rhombic faces meeting. What we can do after we get this shape, this rhombic dodecahedron, we can also make it explode. So we're going to have an exploding rhombic dodecahedron. This is made out of 12 pyramids, and they explode, and they form the first stellation of the rhombic dodecahedron, which I personally think it looks like something of the head, like a head of a mace, which is something, if you don't know, it's something you can use to crush somebody's skull, which is a feeling you get when your hotel wireless doesn't work, and and you can't fix the slides you've worked so hard for, and you have to use a visual vomit that's so 2013, and I'm very sorry for the visual torture I've subjected you with these horrible slides, but they're all I had on this topic, even if it's not what I intended to present today. What I intended to present is more like some demos I have on CodePen. And I hope the internet loves me now, because it didn't love me at the hotel. So yeah, this is my profile loading. Ironically, this is not pure CSS. That's JavaScript. And I have an entire collection of 3D solids. So this is one of the things I intended to present today, and I hope it does load. So this starts off as an octahedron, and then you can cut from the vertices. Now it gets back to the octahedron. So this is the initial shape. And you start cutting from the vertices, and you open up squares at the vertices, and you cut even more. And now you got this thing, which is called a cube octahedron. And this thing, intermediate, is a truncated octahedron. I can't believe I closed that. Okay. You can also do something called expansion. And this is a regular dodecahedron. It also has 12 faces, like the rhombic one, but in this case there are regular pentagons, which you pull outwards, and you open up triangles at the vertices, and you open up squares in between the angles. And if you crash it, you get another shape, which has 20 triangular faces. And something else you can do shapes with shadings and shadows. So this is a tetrahedron, and it has some lighting and shading and shadows. And something else you can do in 3D are 3D surfaces. For example, this is another solid, and this is a torus. Load, please. Okay. And it's not just sitting there, it's also twisting. And since I've stretched the time, I'll end up with a stretching demo, which is also, again, pure CSS. And it's not a solid, but it's a surface. Stretchy surface. Stretchy mesh. Come on. It's stretching it even more. Okay, now it worked. So this is the last thing. Yeah, thank you.
We have time for really one quick question.
Hi, Anna. Awesome talk. I wonder, how do you get a perspective for your shapes? Is it something coming in CSS?
I'm using the CSS property perspective, which you set on the parent of the shape. You can set it on any ancestor, and that's going to work in Chrome. However, it's not going to work in Firefox or IE. With IE, it's a bit tricky because IE doesn't support the preserved 3D value for a transform style. And you can work around that by chaining all the transforms from the parent onto the faces. So if you want to rotate the entire shape, you have to chain that rotate in front of all the transforms for the faces. But if you want to animate that, it means you're going to have a different set of keyframes for all the faces, because each of the faces has a different set of transforms of its own. You can't just have one set of keyframes just for the parent. You're going to have one set of keyframes for every face. And if you have a shape that has something like 100 faces, I have one. It's a snap dodecahedron on my CodePen profile, and that one has 92 faces. I'd have to have 92 sets of keyframes to animate that instead of just one. So, which is why I usually mention for my demos, this does not work in IE, because I'm way too lazy.
All right. Thank you, Anna.